Hello students. We are going to start the article of the moment of inertia today. See, we are into the article of the rotational motion, and the rotational motion has four key component parts of it. The first part of it is supposed to be the center of mass, which we have gone through in detail. The next step is the moment of inertia, which we are going to begin today. And there are two more parts of it, that is a torque and angular momentum. That's what the rotational motion bifurcation is there. And then of course we can wander into the rotational motion behavior and the rolling motion. But before that, you have to venture into these four articles, which are the four tombs or the four pillars of the rotational motion. So we are into the second pillar, that is a moment of inertia. So let's enter into the moment of inertia. Now, what exactly is a moment of inertia? The moment of inertia is made up of two words, the moment and inertia. Now, when we are talking about moment, M-O-M-E-N-T, or moment as we pronounce, the moment is dedicated to the article of the toppling, tipping, rotation, and we have only two kinds of such moments. One is supposed to be the clockwise and second is supposed to be the anti-clockwise, right? It's separate from the term movement. The movement as a term is dedicated when you are leisurely walking. That's known as a movement, or basically in a linear motion we use the term as a movement. And this is the moment. Moment of inertia, that means we have a mass, we have an object, we have a rigid body, and which is in rotation. So it can have a clockwise rotation or an anti-clockwise rotation, and that's basically known as a moment. Now, what is inertia as a property? What is inertia as a property? We say inertia is something which has an ability to resist. Sometimes we say an inability. And why do we say it to be an inability? Reason, because an object by itself, due to its inertia, is not able to change its state by itself. And so it is termed or coined as an inability. But then, it is also supposed to be termed as an ability of resistance towards the motion. So if something has a higher inertia, they have big box, heavy metal iron box full of the stuff inside, and you want to push it, it does not move. Reason, it has a higher inertia. While an ordinary cycle can be easily pedaled, but a car cannot be easily pushed. The reason is, once again, a car, a train, a truck cannot be easily pushed. The reason, high inertia. So we are well versed with inertia. And we know the idea. There's a resistance. Heavier the mass, lesser is acceleration, and that's what is an idea of the inertia. And today that inertia is brought into rotation. So will not it try to resist that rotational motion? Yes, it should. If it is opposing the linear motion, it must oppose the rotational motion also, but both the kind of the motion have different characteristics. So they have different analogous terms, like we have a linear displacement and angular displacement. We have a linear velocity, we have an angular velocity, we have a linear acceleration and an angular acceleration. Which means a kind of analogous behavior, but different terms have been coined in the same mannerism. We coin a different term over here representing inertia, and that term is defined as a rotational inertia, and also termed as the article heading over there, the moment of inertia. So let's venture into the article. Let's get into this article now, that what exactly is the moment of inertia. It comes from the theory of moments. What is the theory of the moments? Let me mention. It's a theory of moments, and the theory of the moments suggests the three terms. There are three terms in this. First of all, is defined as a zeroth moment. Next one is the first moment, right? That's the first moment. And then we have the second moment. And these are known as the moment of mass. The zeroth moment of mass, the first moment of mass, and the second moment of mass. M-O-M-E-N-T, moment. Now how do we write it? We write the zeroth moment of mass as equal to basically integral r power 0 dm. The power of the r is 0. That means you are only dedicated about the mass and you are not dedicated about its position. The moment of mass generates, that's r power 1 dm. That's the first moment of mass. That means r power 1. It also delivers to you in the future article as the first step towards a torque. The first step. Like if you multiply this by g, we get mg into r perpendicular distance maybe. And we have the first step towards the calculation of the torque. And then to generate an idea of the acceleration and angular acceleration, we require the second moment of that mass, which means that is a second power of that r, right? So that is 0, 1, 2 and the dm. But that's a 0th moment of mass, first moment of mass, second moment of mass. This term, the second moment of mass, is defined as I. And what is I? That term is defined as a moment of inertia from the theorem of the moments. Let's see. This one, r power 0 is 1. So that's the integral dm. And that's basically nothing but m. What is m? The mass of the rigid body, the system of particles. The complete mass of the system. And this term, integral r dm. What is integral r dm? That's a moment of mass. We know that. See, if I write the position of the center of mass, can I write this as integral r dm upon integral dm? Yes, I can. Integral dm means what? R power 0 dm. This means this term in the numerator is what? That's the first moment of mass. That's the first moment of mass and divided by, what is it? The 0th moment of mass. That's the 0th moment of mass. So that's what is the theory of the movement, step-by-step movement. First of all, what do we read? The system, the net mass of the system, and then the moment of that mass, that means the rotational effect of that particular mass, and then we are moving into the Euler's law or the Newton's second law in the rotational mechanics and dealing with angular accelerations, and then we venture into this article of the moment of inertia. So moment of inertia, what is the moment of inertia? That's I. And what's the expression? I've shown you. That's the expression. If you have discrete number of particles, this is for large number of particles. A rigid body has large number of particles, of which we select one particle. We select one particle. We divide that rigid body into identical many particles, and then we select one of the particles. So we select one of the particle over there, that dm, and the perpendicular distance of that particle from the axis. This is the axis of rotation. So the perpendicular distance of that particular particle from that particular axis is labeled as r. So the moment of inertia of this particle is written as equal to dm into r square, where r is basically the perpendicular distance of that particle from the given axis. And then there will be different more number of particles, and every particular particle will have a different distance inside that particular object. So let's say there is another particle over here. This will be having some different distance over here, right? And more particles over here. So what do? We integrate this, we integrate this expression, and what do we get? We overall moment of inertia. That's overall moment of inertia of this particular rigid body. Now what is the moment of inertia? We mentioned that the moment of inertia is the resistance. Is the resistance of an object. And that object which we are studying over there is supposed to be a rigid body. So that's the resistance of a rigid body towards the rotational motion. Towards the rotational motion, and that's the idea. That's the idea of the moment of inertia. We'll be very soon learning an expression analogous to F equal to ma. Right? Analogous to F equal to ma means instead of force, we'll be using a symbol torque. This symbol is for torque. Instead of m, you will be using I. Instead of m, I will be using I. And instead of a, I will be using alpha. So what is a? The linear acceleration. What is alpha? Angular acceleration. What is m? Inertia. Linear inertia. And what is I? The rotational inertia. So this term moment of inertia is also coined as rotational inertia. Well, that explains to me quite easily. It's a resistance of the rigid body towards a rotational motion. Higher is supposed to be the moment of inertia. So higher is going to be the resistance, which means from here, the alpha is equal to torque upon I. So I is higher, alpha is supposed to be lesser. So we'll have a more control of an object, on the rigid body. If it accelerates very fast, it's difficult to control. If it accelerates slow, it's easier to control. So as the things are going to pass, what you will find? You will find that as the moment of inertia increases, it's better for us. It's basically how the objects rotate, how easily the objects rotate. Which means suppose I have a pen like this, okay? And I can move it like this. I can rotate it like this, fiddle it like this. And then I can try to move it like this, holding it from here and moving it like this. Okay, with the same firm grip, I hold it from the center and try to move it. Okay, and then I hold it with the same grip over here and then try to move it. So which will be easier? If I hold it from the center or if I hold it from the end. So it will be easier. So you have seen your doors. You've seen your doors, and the doors are supposed to be hinged at the center or from the end. So in our households, the doors are hinged at the ends. And why? If you visit some amusement park or you visit like a metro stations, you find they are hinged at the center. So what happens inside in our homes? It is we are in comfort. We want the things to be in comfort. So it's comfort. It's comfort over there. And while you are at the metro station, what happens? There people are not supposed to be in the comfort. People rush towards the gate and to basically block them, such that one at a time is able to pass. We provide that center hinge over there. So it means that in a very simple mannerism, more free a particle is, higher will be the moment of inertia. Now what's that? That's a very simple. See this. I am holding the pen from here, right? And this is a particle. This particle is at a distance of how much? L by 2. Correct. And so perpendicular distance of the particle, this is the farthest particle from here. Farthest particle at L by 2. So the maximum particle moment of inertia can be m into L by 2 whole square. Of course, this particle will be further closer, right? Suppose I hold it from here, then what happens? With the same particle, see, it's the same body, but I have a different axis now. I have a different hinge now. Now this particle is relatively free. Previously, I have hinged it here, so this particle was at a distance of L by 2. And now if I am hinging it here, this particle is at a distance of L. That means it has become relatively more free to rotate. And that might be also the reason that the handles are provided at the ends of the door. The particle is easy to rotate, easy to move, and hence it must have the higher moment of inertia. So higher moment of inertia also gives me an idea about the higher freedom to rotate. Easy one, right? In the easy mannerism. See, there are formulas, there are concepts, and then there is an easiness of understanding also in our mind that what exactly are we reading. That's what briefing I have given to you. And now we are also going to venture into what's the definition. It's also known as a mass moment of inertia. That's what exactly I have given you the theory. It's basically the zero at first and the second moment of mass is known as a I. It's angular mass or rotational inertia, I mentioned you. That is basically analogous behavior. Like whatever role is M playing in the linear motion, the same role the I plays in the rotational motion. Both of them oppose. Higher mass opposes linear motion and a higher I opposes the rotational motion. Simple. Now further. That's exactly what is written. Similar to how mass determines the force needed for a desired acceleration. Right? So whatever role M plays over here, I plays in the rotational motion. So let's move further. And first of all, introduce to ourselves the AOR. What is it? AOR. What is AOR? That defined as axis of rotation. So everyone look up to the god, no, at the fan. So just look at the fan. And the fan rotates. And the fan rotates about something. What's that? That's an axis. And where is axis? In the case of the fan, it is passing from the center. It's passing from the center. In the case of the door, it's passing from the end. Two of the live examples which everyone can find at their respective homes. Right? So two of the lives are examples. There will be many more, umpteen number of examples. But these are supposed to be the easiest one. You can rotate the what? Regulator of the fan. Regulator of the fan. You can also rotate the steering of the car. You can also rotate the nut bolt of the wheel of a car. You can open up the tap, and that's the rotation. So there are different. You can open up the screw with the help of a screwdriver. So these are many different kinds of the rotation you can observe around you. Two of the finest and the easiest I have mentioned, and I have mentioned both of them because both of them deal with a different axis. One of this is an end axis, and second is a center axis. The fan with the center axis in this case. That's the center axis. It's passing through the center mass. Oh, that's the COM. And this axis is passing through the center mass of it. Not in the case of the door, my dear. Not in the case of the door. The center mass of the door lies somewhere here. But the COM is not passing through this axis of rotation, AOR, axis of rotation. So we can have the different axes, like in this case of a disk. We have this as a center mass, that's the COM, and the axis is passing through this. Then what such an axis should be known as? Such an axis will pass through the center mass and is perpendicular to the plane. Repeating again, an axis which is passing through the COM and perpendicular to the plane. Such an axis is defined as centroidal axis. That's a centroidal axis, and there can be this axis also. What is this axis? This axis also passes through center mass but isn't perpendicular to the plane. Such an axis is known as COM axis. So there can be many center mass axes. In fact, this is another axis which is passing through the center mass. But that's also COM axis but isn't centroidal. Centroidal had two features. One, definitely passing through the COM, and the second, perpendicular to the plane of the motion. Where is it? It's rotating here. So the axis is perpendicular to it. Correct? Clear? Right, of course. It is there. Right, so this is supposed to be the plane. Axis which is plane perpendicular. The axis which is plane perpendicular and passing through the center of mass. That's the centroidal axis. So axis which is plane perpendicular and through COM. That's your centroidal axis. So you'll get many questions based upon the centroidal axis. And of course, about the other axes also, but I said many questions based upon the centroidal. But this axis, see this axis, this is not passing to the center of mass. This was a centroidal axis, not this one. So this is a non-centroidal axis. And this can be given many names like this. Now in this particular case, it is plane perpendicular in this case and passes through the edge of the disk. So you can also say it's a rim axis, like it's passing through the rim. So it's a rim axis and it's perpendicular to the plane. So the questions will try to give a different name and try to illustrate that what kind of axis is there. Let's see, the question may say in this language as calculate a moment of inertia about an axis passing through the rim point and perpendicular to the plane. But that's obviously their axis. Clear? Right? So it can also generate an axis like this. And this particular axis may be known as what? It is again an axis passing through the rim point, but in the plane. That's in the plane. So it is in the plane. This particular axis is supposed to be in the plane. So these are the different axes, right? This becomes a different axis. And that's in the plane. And this appears to be like a tangent. So it can also be mentioned as a tangent axis. So the question will give you enough language such that you're clear that about which axis we are dealing in a particular problem. Every problem will be different. Like a door problem and a fan problem are different. So every problem is going to be different. So you need to analyze first of all AOR. And as for the AOR, then you are going to look into where are the particles? Where are the particles means what is the distribution of the particles? Yes, my dear. Hitting the strong word. That you need to check the distribution of particles about the given axis. Let's assume that this is axis. So this is the axis and this is a rigid body. So there are the particles over here M1. There is a particle over here M2. There is a particle over here M3. And the distance of this particle from here is R1. Distance of this particle from here is R2. Distance of this particle from here is R3. So all the particles are distributed in a different mechanism about this particular axis. The object is same, the rigid body is same. Assume the same rigid body, but an axis which is outside the body or somewhere else, not passing exactly through the same position. So now it's a different axis. Let's say this is supposed to be the axis as PQ, and let's say this is an axis as RS. So you have the same particles, these are same particles over here, let's say, but they have a different distance now from here. Different distance. That means when you're calculating the moment of inertia about the PQ, so for this particular particle, you will have M1 into R1 square plus M2 into R2 square plus M3 into R3 square and so on. But over here, these distances are different now. That is R2 dash for M2 particle. That is R1 dash for M1 particle. The distance has changed from the respective axis. So, the moment of inertia about this particular axis, RS, will be different. See, the mass is same. The shape of the object is same. But the axis is different. And therefore, the moment of inertia, that is M1 R1 dash square, M2 R2 dash square and so on, the moment of inertia is turning out to be different, is going to behave differently about the different axes. As I said, if I rotate this about the center and if I rotate this about the end, it's altogether different behavior. And that's what the moment of inertia basically depends upon. It depends upon AOR. So before reading the moment of inertia, it was eventually essential to mention what is AOR. Right? So now we venture into the article further. In the moment of inertia. The first of all, I will love to write the factors on which the moment of inertia depends. I would like to mention these factors on which the MOI depends. The first is supposed to be the mass of the rigid body. See, we will be dealing with the rigid bodies only in our question here. So directly hit the point now. So we are going to deal with the mass of the rigid body. Higher is a mass, higher is a mass, higher is a moment of inertia. Of course it is. Inertia means that only. See, heavier an object, higher is the inertia. So that's exactly the first point. See, it's different from COM. In the center of mass concept, we said the COM does not depend upon the overall mass, but definitely depends upon the distribution of mass. So this idea is slightly different. In this, it depends definitely upon the mass. So there are two objects of the same shape, that means the same distribution, but one is having a higher mass, it will be having a higher moment of inertia. Of course, I talked about the shape. But the second, it depends upon the distribution of mass. So that same article which comes up, like how the mass is distributed at edges of a triangle, or the edges of a square, or the corners of a square, or like a ring, or like a disc, or like a sphere, or like a cylinder. So how we have distributed that mass is going to be very, very important. And then the third, actually second and third point are going to be same. But then we like to make it a different note. Reason, because this is something new which we were not studying in COM. But we are studying right now. And what's that? AOR. So the moment of inertia definitely depends upon the axis of rotation, as just now mentioned. The distribution is different. See, if I am taking the center axis, the distribution is different. This is an L by 2, this is an L by 2. But if I am taking over here, then what is happening? This particle has zero moment of inertia. Reason? This has zero moment of inertia. Reason? Because it lies on the axis. It lies on this axis. So the perpendicular distance is zero. But this particle has a very high moment of inertia because it is at a distance of L. Correct? So the moment of inertia enhances because on an average, all these particles which are here, have more than L/2 distance, and beforehand any particle was not having more than L/2 distance. Correct. So AOR becomes important. The shape is same. The shape is same. The distribution is same, but the axis changed. Oh, the pen also gone. So the axis changed. And any other factor. Any other factor. We say this is a factor basically, but then we will have to say the shape factor. So the shape factor. Then what is the shape? The ring moment of inertia, disk moment of inertia, sphere moment of inertia will be different. It will be different. So the shape factor will come into play, and we will be coining a term also. And a term will be defined as K, and K will be mentioned as radius of gyration. The radius of gyration. That will be termed as a point K. Later on we will study to that also. So these are the factors on which the moment of inertia depends upon. To make it simple, the moment of inertia is written as m into k square. So actually it depends upon just the two terms, m and k. Where m is the mass of the rigid body, overall mass, and k is supposed to be the radius of gyration, and radius of gyration depends upon the shape, axis and distribution. So all these factors are clubbed into this. The AOR and the distribution is clubbed into what? K, right? We'll be coming to the K part later on in the next part of the lecture, not today, okay? So, how do we write a moment of inertia? So, in an easier manner, for discrete distribution. So, for the discrete distribution, how do I mention the moment of inertia? The moment of inertia is equal to, for a discrete distribution, m1 r1 square plus m2 r2 square till mn rn square and so on, which can be also written as equal to summation of mi ri square, I value ranging from 1 to n. If it is a discrete distribution, means number of particles are counted. We have an octagonal arrangement, or we have a hexagonal arrangement, or we have a triangular arrangement or a square arrangement, at every corner of which we have a particle. So you can count 8 particles, 6 particles, 3 particles, 4 particles respectively, and calculate the distance of each particle from the given axis. Of course, AOR will be important, and so you can easily calculate a MOI easily, right? So we have the illustration in front of us, over here, where this is a bar, at the ends of which we have the masses, and we are neglecting the mass of the bar. Of course, it is not neglected in the real sense. If you use that for the lifting, you find that without the weights also it is pretty heavy. It's made of steel or iron and is very heavy. But right now we are neglecting it, okay? So we have the masses here and here right now, okay? So we are assuming this to be the massless. This as a massless, and we have a rod which is passing through, we have an axis which is passing through the center. We need to calculate the moment of inertia about this. Okay, so let's calculate the moment of inertia about this. So this particle into this distance, perpendicular distance, how much it is, r? So what is the moment of inertia? That becomes as m into r square. For this particle, it's again the same perpendicular distance, that is r, that is plus m into r square, and the result becomes 2m into r square. That's the moment of inertia about the center. Now, if I change it and take this axis, what is this axis? It's an end axis. It's a center axis. See, it is also the center of mass of it. This is m and n. So this is also COM. Right? It's COM, and it is perpendicular to this plane. So the moment of inertia about this axis, let me write ICM over here, that is equal to 2m into r square. Right? But this axis is not passing through the center of mass. The COM lies here. So it's a different axis. I can mention this as an end axis since it is passing through the end. Now, what is the moment of inertia of this particle? 0. Reason, it lies on the axis, so the perpendicular distance is 0. That is m into perpendicular distance square. What about the second particle? It is plus m into perpendicular distance. How much? 2r. This distance is 2r from the axis. So what's the moment of inertia? That becomes 4 mr square. How much? 4 mr square. This was having 2 mr square. That is having 4 mr square. Which is more? That one. And that's what I explained to you beforehand also. That if I take it from the center, then the moment of inertia will be lesser. But if I take the axis at the end, this particle will be relatively more free. It will be at a farther distance, and therefore the moment of inertia will become stronger. In fact, if you pass the axis anywhere else, let's try. So I have these two masses, and let's pass the axis from here. Let's take the axis as this one, and this is at L by 4 from here, and 3L by 4 from here. Correct? And let's calculate the moment of inertia about this axis. Let's mention this as a PQ axis. So the moment of inertia about a PQ axis should be equal to, that is m into 3L by 4 whole square of this particle distance from the axis. And for the second particle, that is m into L upon 4 whole square. Correct? So that works upon as equal to m. Let's see, in this case, since the distance is 2r over here, so let's take the terms according to this only. Let's take the terms according to this only, such that we are able to relate to this article only. So let's take the distances at 2r. So let's divide the distance as this as r by 2 and this as 3r by 2. Correct? Right? So it becomes 2r complete. So that is m into 3r by 2 whole square and plus m into r by 2 whole square. Right? Now check this. This becomes 9 mr square by 4 and plus from here mr square by 4. So that becomes 10 mr square by 4, and 10 by 4 will be 2.5. That is 2.5 mr square. How much? 2.5 mr square. Still it is coming more than ICM. More than this value. This value is still more than ICM. So see, if I take an axis somewhere here, outside here, so definitely the distance will more increase. It will increase. So to create a maxima is not an issue. But there is a concept of minima. And out of these arrangements of the axis, the different axes which you are predominantly checking, you can comment, my friends, that the moment of inertia is coming minimum about this axis, the minimum about the centroidal axis over here. So for all the possible axes over here, we get this moment of inertia to be minimum. Maybe this language is going to crack down on a question. Let's check this out. Where we have the question like this. It says 2 point masses and m1 and m2 are joined by a weightless rod of length r. Calculate a moment of inertia about an axis passing to its center of mass and perpendicular to the rod. So there are two particles. One of them is m1, the second particle is m2. And it's a weightless rod. And the length of the rod is given as equal to r. And the question says, calculate the moment of inertia of the system about axis passing to the center. No, center of mass. And the center of mass is not at the center. The reason? Equal masses are not there. Which means, first of all, we must know where is the center of mass. If m1 is more than m2, assumingly, then center of mass is closer to m1. This much we know. And so the axis is supposed to be perpendicular to the rod, this one, and passing through this. So that qualifies as the center of mass axis or the centroidal axis. Can the moment of inertia of a center of mass axis be 0? Yes, it can be. See, you can create an axis like this. It will be passing to the center of mass, but both the particles will lie on that axis. and therefore the moment of inertia can become 0. Correct? So this is a centroidal axis which is passing to the center of mass and perpendicular to the rod over there. So we can rotate this in this plane horizontal, and the axis is perpendicular to this. Right? We can rotate this horizontal and the axis is perpendicular to this. Correct? Okay, now we need to calculate a moment of inertia. So we require the distance r1. The common mistake what the students can do at a prelim level, initial level, learning level, what they can do the mistake is that take the axis from the center. So it's very clear that the axis is not through the center and it's through the center of mass. Correct? Very correct. So now calculate the answer. So the moment of inertia about this axis is equal to m1 r1 square and plus m2 r2 square. Now there is a difficulty. There was the value for r1 and r2. For that, we can apply the center of mass concept. That is m1 r1 is equal to m2 r2. That's it. And further, r1 plus r2 is supposed to be equal to r. This one plus this one is equal to r. And center of mass phenomena. m1 r1 is equal to m2 r2. Those who don't know that need to watch the previous lectures of center of mass. Now, r2 from here can be written as r minus r1 and we place in this equation. So you get m1 r1 as m2 into r minus of r1. So this r1 comes here. That becomes m1 plus m2 into r1 is equal to m2 into r. So the value for the r1 that works m2 into r divided by m1 plus of m2. That's the value for r1. If we substitute this particular value over here and subtract from r, we'll get the value for the r2 that will be m1 into r upon m1 plus of m2. That's the values for the r1 and r2 produced very easily from the COM concept. Why we were able to apply? Because the question gave us the idea that axis is through the COM. So COM concept is applicable. Fine. Now see, even this R1 and R2 are easy to understand. It's kind of an internal division formula. And we have already said, let's say we have the mass at 2m and n. So the ratio of the mass at 2 is to 1. The center mass will be at a distance of 1 is to 2. Reverse. m1 r1 equal to m2 r2. M is proportional to 1 by r. So mass ratio 2 is to 1, center mass distances will be 1 is to 2. So one will be r by 3 and second will be 2r by 3 like that. So internal division. Same way. What about this distance? That is m2 into r upon total mass. m2 into r. And what about this distance? m1 into r upon m1 plus m2. That's what the result is. In r1 we have m2, in r2 we have m1. That is simple internal division formula. And now, once you have got the value, substitute here. So the moment of inertia of the center mass becomes equal to m1 into r1 square. Square it the term. That is m2 square r square upon m1 plus m2 whole square. That's placing the value for the r1 from here. Then the second term. That is plus m2 r2 square. Square of it. So m1 square r square divided by m1 plus m2 whole square. Clear? Very clear. Axis is not passing to the center, is passing to the center of mass. Rightly done. Rightly done. Okay. And then we take common. What common? m1 is common, m2 is common, r square is common, m1 upon m2 whole square. This is common. Everything is common. No. From here m2 is left and from here m1 is left. Oh, this simplifies. It simplifies. It simplifies into a result where this cancels out with this and we receive the result m1 m2 upon m1 plus m2 and into r square. That's your expression for the moment of inertia about the center mass axis. About the center mass axis. So nothing special about it, or there is something special about it. There is something special about it. And what's that? This term m1 m2 upon m1 plus m2 is written as mu. Is written as mu, and you will say it's a coefficient of friction. No. Mu over here is defined as a reduced mass. It's a reduced mass. I will be dealing with the reduced mass in detail in the COM frame concept. I will be dealing that separately in the advanced lecture. And that's a reduced mass. Reduced mass is nothing but a combination of mass. Exactly what kind of a combination? It's like this. 1 upon mu is equal to 1 upon m1 and plus 1 upon m2. That's exactly what it is. If you will calculate this, you will receive this as m1 m2 upon m1 plus m2. So that's a simple combination of masses. Actually, why do we say it to be a reduced mass? A reason. It basically reduces a binary system into a single particle system. Two particle system into single. Like, we will always like to say that the earth moves around the sun, but in practicality, the earth and sun move around a common center of mass. But then we like to say that the earth moves around the sun. So to attain that idea, that the sun to be stationary, and the reason for that will be that the center of mass lies inside the sun, and the sun motion is not visible, and only the earth motion is visible. That means the mass which is lesser, its motion is visible. Getting the point? See, the earth is lighter than the sun. Similarly, electron is lighter than nucleus. Much lighter. So then the heavier particle motion is not visible. That does not mean it's not there. It's there, but it's not visible to us. The reason because the center of mass is too close to it. So it's easier to study a single particle model then. Like the Neal Bohr theory is a single electron model. It's easier to study the single particle model. But actually we have the binary particle model. So when you reduce it from the binary particle model to a single particle model, that is known as reduced mass. So it's a combination of mass and this is the value. So the moment of inertia can be written as mu into r square, kind of a good enchanting formula to memorize for our flashcard. Mu into r square, simple. Good one, right? And we've got two things for the two particles. This one is one thing. This result will only come when the axis is COM axis and perpendicular to the plane. Then this result is there. Correct? It's not a center axis, it's a COM axis. And we have gathered one more fact, that the moment of inertia is going to be minimum about the centroidal axis. Right? So two facts we have gathered for the binary systems. Let's move ahead and try to calculate a numerical base upon this idea. Like, read the question carefully and maybe we are able to solve it quick time. The question says there are two point-sized bodies. The masses are 20 gram, 30 gram. Fixed at the two ends of a light rod of length 1.5 meter. The moment of inertia of these two bodies about an axis perpendicular to length and passing to center of mass. Center of mass. So that means once again the question is, that is a 30 gram particle and this is 20 gram particle and the length of the rod is 1.5 meter. So where is going to be the center of mass, my friends? The center of mass is going to be over here, closer to the heavier particle. What is the ratio? The ratio of the masses is 2:3. How much? 2:3. So the distance should be in the ratio 3:2, reverse. 3:2, correct? That means this distance should be 3/5. That's 3:2. So total parts is how much? 5. And this is the 3 parts of that 5. So 3/5 of 1.5 meter. That should be the location of the center of mass from here. How much is that? That is 0.3 into 3. So 0.9 meter. So the remaining, this one, that becomes 2/5 of 1.5. Correct? 2/5 of this value. So 2/5 of this. So that's 0.6. So that's 0.6. So if this is the axis, so we got the perpendicular distances. And we can calculate the moment of inertia about this axis. So what is that supposed to be equal to? 20 gram. So 20 into 10 power minus 3 kilogram into distance square. And that's 0.9 square. So 0.9 square. And plus that's 30 grams. So 30 into 10 power minus 3. And into 0.6 square. That's it. We solve this. Let's see what's the value. That becomes 81 into 2. So 81, 0.81 into 2. So 0.81. That becomes into 10, 8.1. 8.1 into 2, so 16.2 into 10 power minus 3 and plus 0.6 square 36.36 exactly into 10. So 3.6 into 3. So 10.8. So 10.8 and into 10 power minus 3. We add them, we'll get 27 into 10 power minus 3 kilogram meter square. That's a simple mr square, kilogram meter square. Do we have somewhere as an answer? It stands here. It can be written as 2.7 into 10 power minus 2 kilogram meter square, and so that beautifully fits the B option. Sir, can we use a formula? Of course you can. Which formula? Which we derived over here, mu r square. So you can save your time. You can save your time. Of course you can solve it like this also by locating the center mass, but beforehand also you can solve it like m1 m2 upon m1 plus m2 into r square. So about this axis, so that's 20 gram. So 20 into 10 power minus 3 into 30 grams. So 30 into 10 power minus 3 into 1.5 square and divided by 20 plus 30, 50 grams. So 50 into 10 power minus 3. This gets cancelled and you calculate this, you will still get the same value, that is 2.7 into 10 power minus 3 kilogram meter square. So you're just saving your time, I think some 10-15 seconds basically, or 30 seconds for locating the center mass basically. You say no need of locating the center mass because it has been already done while deriving this particular result. So good one, okay, good one. So let's move forward. And I have a question over here, and the question is, which of this is having a higher moment of inertia? There are three particles. Which of this is having a higher moment of inertia? And now see, sometimes we misinterpret the things. As I said, so this particle is having a higher moment of inertia if the axis is here. But if the axis is here, then this is having the higher moment of inertia. Then the reverse question. If this is the axis from here, then this particle or this particle, which has a higher moment of inertia? So we will say, so this particle because the distance is more, and this particle has lesser moment of inertia because the distance is less, but then we did not check in the mass. As I said, the moment of inertia depends upon the distribution and as well as the axis and as well as the mass also. So if I check for this particle, for the first particle, so that I1 is equal to 36 into 1 square, that's 36 kilogram meter square. If I check for the second particle, that is 9 into 2 square, m into r square, so that's once again 36 kilogram meter square. And if I check in for the third particle, that's 4 kg particle, it's a 4 kg particle, so that's 4 into 3 square, that's once again 36 kilogram meter square. That means all the three particles are having the different moment of inertia. No, identical. They were having a different distribution. They were having a different mass, but something is same, the moment of inertia. So all of the objects have the same MOI. I will like to say MOI, moment of inertia. AOR, axis of rotation. COM, center of mass. Conservation of linear momentum. COM, good abbreviations. Alright. So अब हम मतलब लेवल बढ़ा रहे हैं, बहुत ज़्यादा नहीं, we are not increasing by much, we are just elevating ourselves from 2 to 3 particles. So we have 3 point masses here, and the masses are given as 3, 2 and 1, and ABC, this is A, this is B, and this is C, and AB is given 0.3 meter, and AC is 0.5, and BC is 0.4. So this cannot be a triangle because it's a Pythagorean triplet. But after seeing only we get to know. So then the triangle has to be like this. So that's the triangle. And who is A, who is B, who is C? Check that. AC is 0.5. So this has to be C and this has to be B. Where AB is 0.3 meter. This is 0.4 meter then. And AC is 0.5 meter. And this angle is 90 for sure. And then we have the masses. So we have the masses. Let's see where the masses are kept. At A, we have a 3 kg particle. At B, we have 2 kg. So over here, we have a 2 kg particle. And over here, we have a 1 kg particle. That's all. And this is the construction. And MI, MI seems to be the phones, right? So MI, moment of inertia, MOI bolna chahiye, about an axis through A. So axis is through A, and normal to the plane. Normal means what? Normal means perpendicular. So perpendicular to this what? Perpendicular to this what? Perpendicular where? Outside or inside? So I have a demarcation to explain that. I have a symbol to explain that. What? Either a dot or a cross. A dot or a cross. And what's a dot? A dot is supposed to be pointing inside. No, pointing outside. Pointing outside like this one. Like an arrow. We have seen an arrow. So we throw an arrow. We release an arrow. So an arrow is having a cross at the back and a spearhead, an arrowhead at the front. So if you look at it, you will see a dot coming towards you, and if it is moving away, you will see a cross going away from you. Correct? And both of them are perpendicular. This is perpendicular to the plane. But perpendicular to the plane, this is known as outwards, and this is known as inwards. Right? Outwards and inwards. It does not make any sense right now because we are just talking about an axis which is perpendicular to the plane. So you can either use a cross or a dot, does not make any difference. So I am literally making a cross over here. Explaining the axis is supposed to be plane perpendicular. Correct? Axis is plane perpendicular. Simple denotation, right, my dear. And we need to find a moment of inertia. So let's start and calculate about this axis, about a cross axis. That is first particle, that is 3 into 0 square, because that particle lies on the axis. This whole thing can rotate except this mass particle because it's lying on the axis, so it's no freedom to rotate. Everyone has a freedom to rotate. Some has large, some has less. This has got no freedom to rotate. Zero moment of inertia. Which one has the highest moment of inertia? C. C1, because it's a maximum perpendicular distance. So it's not perpendicular. It is. This axis is like this, my dear. Like this. Like this. So this angle will be 90. So this is the perpendicular distance from this axis. Getting the point? That's a plane perpendicular axis. And so this will be the perpendicular distance. That's 0.5. So that's 1 into 0.5 square. And for this one, once again, this is axis and this is the perpendicular distance. So that is plus 2 into 0.3 square. That's it. That's it. All the three particle perpendicular distances are over. And let's see what do we get. That's 0.25. Ye to 0. This is 0. And what about this? 0.9 into 2. That's 0.18. 0.09 into 2. 0.09 into 2. 0.18. So that's 8530. So 0.43. So 0.43 kilogram meter square. Out to be an option. Out to be an option somewhere. A part itself. So we have elevated ourselves to the three particle system also. Let's move ahead. So now it's a simple one. Looking simple, there are 3 point masses M1, M2, M3, vertices of equilateral triangle. Now we are sure that triangle is like this. This is M1, this is M2, and this is M3. And this is an equilateral triangle. Side length is A. What is the MOI of the system about an axis along the altitude and passing through M1? Altitude and passing through M1, so this must be the axis. This is an altitude and passing through M1. So M1 moment of inertia becomes 0. Reason, it lies on the axis. M2, this is a perpendicular distance. How much? A by 2, half of the side length. M3, perpendicular distance A by 2, half of the side length. So what's the moment of inertia about this axis? That's an altitude axis. What's the moment of inertia? That is M1 into 0 square plus M2 into A by 2 whole square and plus M3 into A by 2 whole square. What is the result? That becomes M2 plus M3 and into A square upon 4. That becomes the result. Simple. Very simple. The result over here. Triangular distribution, different kind of questions can be created. There and then, as per the merit of the question, we are going to solve it. There is no memory. There is no memory. Every time the axis changes, the distribution changes, and then you have to recalculate the moment of inertia. Right? The next one. The next one, oh, there are 4. So we are increasing our level more. We have 4 particles now. 1, 2, 3, 4. This is capital M, this is small m. And capital M is more than small m. The question says that. And A is equal to B is given that. It says, which of the coordinate axes? This is X, this is Y, and that's Z, which has the smallest and the largest MOI. So let's calculate one by one. So let's calculate for the X axis. So this one goes off because it lies on the X axis. So perpendicular distance becomes 0. This also goes off, but it goes off in the sense uska freedom is lost. His freedom is lost, and the moment of inertia becomes 0 because it is lying on the axis. So that's 0 plus 0 and plus. This one is having this much perpendicular distance. How much? B. And this much, same perpendicular distance, B. So that's plus mb square and plus mb square. That becomes twice of mb square. That's for the X. And now we focus on the Y axis. So for the Y axis, this one, moment of inertia of these two goes off. Reason they lie on the Y axis, so their freedom is gone because the perpendicular distance is 0. And these two enjoy the freedom. They can rotate about a Y axis. This can rotate about a Y axis. And the axis means the Y axis over here. And this can rotate about this. Like this. Okay. This can rotate about this. And if this was the X axis, so they can rotate about this. The Y particles. Correct? And if this is the axis, then they can rotate about this. These particles. Correct? So perpendicular axis basically. Now about the Y axis, their moment of inertia becomes 0. These two have m perpendicular distance is a. This one also a. So we have m into a square and plus m into a square. Pardon, m is capital M this time, okay? And plus 0 plus 0. So that becomes twice of capital M into a square. Twice of capital M into a square. And then it comes the Z axis. It comes the Z axis. So let's check for the Z axis. For the Z axis, this axis, oh, none of the particles lie on the axis. None of the particles. And so it is also perpendicular to this. And this axis is also perpendicular to the X, to the Y and X both. So A and B both have perpendicular distance. So the moment of inertia about a Z seems to be maximum for me. That is m into a square plus m into a square. That's a capital M. And then small m. So that is small m into v square plus small m into v square. That's pretty much as twice of capital M a square plus twice of small m v square. And this seems to be the maximum moment of inertia. While since the question says small m is lesser, so the Ix is supposed to be the minimum moment of inertia of all these three, of all the three, correct? And out of this you can locate the center of mass and pass an axis through this, so maybe we get the minimum of all the values. Out of these three coordinate axes we have generated the result. Moving ahead. Graphical question. What's the question like? It says the moment of inertia of a sphere of mass m and radius is I, keeping m constant, if a graph is plotted between I and R. I don't know what is the moment of inertia of the sphere exactly, but I know the format. What is the format? That the moment of inertia is proportional to mr square. I know that, right? It can be 2 mr square, 3 mr square, 1 by 2 mr square. Some factor can be there as we've been calculating. M is kept constant, and a graph is plotted between I and R, so I is proportional to R square. That completes the question. I versus R square, I degree is 1, R degree is 2. The graph is parabolic. It's parabolic and increasing. R increases, I increases. So this cannot be there. It's a logarithmic graph. It's a linear graph. It's a rectangular hyperbola. R increases, I decreases. This gets saturated. R further increases, I does not increase. It is not the case. I is linear function of R, not the case. This is the only correct. It's a parabolic function. R increases, I increases. Correct? Okay. The next one. This seems to be a question, a long question. Say there are 4 identical particles, 0.5 kg each, placed at the vertices of a square. So let's create a square. That's 0.5 kg. That's 0.5 kg. That's 0.5 kg. And that's 0.5 kg. And this all are 2 meter. 2 meter, 2 meter, 2 meter is given. And these are all massless rods. Okay, done, easy. Then what is the MOI? A part about an axis passing to the midpoint of one of the sides. Midpoint of one of the sides. So let's say this point. And perpendicular to the plane. So I can create a cross axis over here. It's passing to the midpoint and perpendicular to the plane. Simple, simple. Now let's calculate the distances and solve it. So the distance of this particle will be how much? That will be 1 meter. Distance of this particle will be how much? 1 meter. So if you write the moment of inertia, that becomes equal to as 0.5 into 1 square. 0.5 is half. So half into 1 square. And again half into 1 square for the second particle. And next for the third particle, this is the distance. The axis is here. This is the axis. And this will be the perpendicular distance. Perpendicular distance, right? So that angle will be 90. So it's a perpendicular distance. And how do we find that? This side will be 1 meter. And this is 2 meter. This one. So Pythagoras, how much is the value? Root 5. How much? Root 5. And for the fourth particle also the same distance. That will be again root 5. So I think we are closed. We have half into root 5 whole square and plus again half into root 5 whole square. 0.5 I have written half, okay? No confusion, huh? Half into root 5 whole square. Just add up. Half is common. We have 1 plus 1 plus 5 plus 5. So that's 12 upon 2. That's 6 kilogram meter square is the answer for the A part. And there is a C part. B is not there. So we make it B. For the B part, axis lies in the plane and passes through diagonally opposite particles. So let's reconstruct the diagram. Now it says then axis is in the plane and is passing through 2 diagonally opposite particles. So that is an axis. That is an axis. So this particle is not free to rotate because it lies on this. On the axis, so no freedom to rotate. This particle again lies on the axis, so no freedom to rotate. While this particle has a definite freedom. How much? The perpendicular distance. And what is that? Oh, it's a square. Square. And the diagonals of the square intersect at 90. At 90. So, what will be this distance? This side is how much? 2. This angle is how much? 45. So, this will be 2 cos 45. 2 cos 45. That is 2 into 1 by root 2. So, 2 into 1 by root 2 means how much? That is root 2. So, the perpendicular distance becomes how much? Root 2. And for this particle, the same. The same for this particle, that is root 2. So I think we can just finish off the question. So about this axis, that is a diagonal axis over here. So these two moment of inertia 0, no freedom to rotate. For them, they are lying on the axis, so no freedom, no moment of inertia, no perpendicular distance. And for the rest of them, that is half, 0.5 I am written half. So into root 2 square. And for the last particle also half into root 2 square. Simple. 0.5 I have written half. So that's equal to how much? Half into, that's 2 plus 2, 4. 4 upon 2, that becomes 2 kilogram meter square as a result. As a value for the moment of inertia for this. Right. So what we have learned today is the intro of the moment of inertia, what the moment of inertia basically is. And I've tried to get into the discrete distribution of the 2 particle system, 3 particle system, 4 particle system. You can enhance it. You can make n particle system also. But that n should be discrete. That means it should be countable. See, you can count up to 6 particle, 8 particle, 10 particle, 12 particles. If it becomes 20 particles, 50 particles, it becomes cumbersome. If it becomes 1000 particles, 5000 particles, 5 lakh particles, then it becomes continuous. So in the tomorrow's lecture, we will be dealing, first of all, as a ritual, some revision of the today's article, some questions, and then we'll be migrating into the continuous objects like a rod, a ring, a disc, a sphere, a cylinder. We'll be migrating into the moment of inertia of these particles. And so we've entered into an exciting article where we are one more step closer to the understanding behavior of the rotational motion. Okay, so kindly please revise your lecture. Try to solve the questions once yourself also. The formula is very simple. Formula is not there. There's a couple of things which we just actually got within the lecture was that the moment of inertia will be minimum about the center of mass centroidal axis. Right? And I depends upon mass of the rigid body, axis of rotation, shape of the body, distribution. In fact, the shape and the axis of rotation or the distribution feature is basically what K. K is what? Radius of gyration. So a shorthand formula will be mk square. M is the mass of the system and K is the radius of gyration. We'll be of course discussing the radius of the gyration also another day, right? So for the time being, have a good day. Bye.